Hello boys and girls. So today's video is another video I throw in before discussing topoi of sets in the von Neumann hierarchy. This video is again one that is constructive leaning, and I want to discuss the proxy power sets in a theory without power sets, right? Because in the von Neumann hierarchy, in which we will discuss next week the classical situation, but there the power set of course plays a major role. There are some thoughts in like constructive Zermelo-Fraenkel frameworks which don't have excluded middle or power set. Stuff that you see here, for example on the slides, this is by Ziegler from a decade ago, some alternative hierarchies that classically are, however, the same as the classical ones. This man also has a PhD thesis online where you could read this thing up. I will, however, not really like just zoom in on the von Neumann discussion here in this video, but more generally discuss also the notion of truth value, this reified truth value in a constructive framework, constructive set theory. I have, of course, talked about power sets in both from a categorical angle and from in general this constructive angle quite a bit in this video, in this in my logic playlist. I saw that here 5 years ago I did a bunch of things that were mostly like topos related, but I also have this sort of trying to explain some of the things that I connect to in this video. Again, I'm pretty sure I'm the only person like repeatedly making videos on this sort of topics, but I think this video will be like fairly easy to follow. I will like mostly talk on the very low level, and we want to get a feeling on this, as I call it, this proxy power set operation, like how much you can get out of basically axiom of exponentiation, the existence of function spaces, and how to understand truth values in that context, the notion of characteristic function that enable this construction that then classically gives you what you know as the von Neumann hierarchy. Here's already a typo. This should be read, not teed. So I will start very softly. There are some warm-ups, right? So again, we are mostly here, now I think completely here discussing things in a constructive framework without power set, but set theoretically. However, we have replacement, which is more complicated to tackle from a category for theoretic angle. And we have function spaces, as I said. The power set axiom would look something like this here, right? You would say for every set B, there exists a set C, the power set, that is such that for every set, if that set is a subset of B, it is in this collection, right? In particular here, the sort of impredicative aspects is that is sort of irked a bunch of philosophers 100 years ago are the fact that these quantifiers here, in particular here, this S is not over another set. So this is sort of reaching over the whole universe, and you deal with like collecting all the subsets of B, which, however, as we will see constructively, a priori like is like a class-like object. It's like a very vast and conceptually complicated entity, right? This is the whole Lie-algebra or category stuff that I discuss in also more this topos inspired way. But here are just some pointers that go in this direction, right? All that you see here on screen is actually completely trivial, but if you have never seen this before, it might help to like take a step back and reconsider all the notions that you oversaw might like crucially depend on having taken on a very like excluded middle based perspective. So consider again some set B, for example, natural numbers is simple enough, but it's already very interesting. any subset A of B, then of course you can consider the intersection of B with A, and since A is a subset of B, this is again just all the elements A you already had. You can write it down like this, right? This is like this comprehension notation, or it's actually bounded comprehension, because it's a subset of B, and you have this predicate here without quantifiers. PA is a predicate that I defined here, and here more explicitly this A is defined as a subset with this PA, right? Or in the other way around, let's say I have by some theory around me, by some context, defined a predicate Q, maybe some arithmetics, can involve a lot of complicated expression, quantifiers, whatever. Here I give some examples. N might be the zero of a polynomial, or more complicated. You have this Collatz function, and N is all the elements where this comes back to 1 or does not come back to 1, whatever. And then again, with comprehension from this predicate, we define a subset of BA. And I just make this very mundane comment here, or to already prime you of thinking these sets in correspondence with these predicates, subsets with predicates, where on the predicate side, there are various questions in math that you might want to ask. Is this and this equivalent, are expressed in terms of these predicates, and if subsets relate to predicates in this simple separation fashion, then the wealth of predicates that are out there, which may or may not equivalent or imply each other in one or the other direction, or do not imply each other in the other direction, they have this sort of complicated structure, and this is what you have with this hiding structure. And the thing is that if you have a weaker logic, the constructive logic, where you can say less about these predicates, then this translates to the structure of the subsets being more complicated. And we will see in this video how this is manifesting itself already by just looking at subsets of the singleton. Okay, and here another warm-up. So I have just defined this symbol, the successor symbol as such, union with the singleton, and I introduce the first few von Neumann ordinals. You know this definition, and in this video I will introduce this notation, because this is what we are going to generalize in a bit, where I write uppercase omega 2 just for this set that holds two distinguishable members. You can think of this as the Boolean data type in programming, and these are basically representing the classical truth values. And of course, if we are talking about set theories that are strong enough so that all function spaces exist, then in particular the set of the class of maps, the class of functions from any set to this two-element set, the Booleans, as I will call them, exists also as a set. And of course, classically, this is just the same as with a little bijection that we will in this video actually see explicitly is in bijection to the power set. This is what we are going to play with and broaden up in the constructive context. Okay, I see I actually play this through here. I don't want to stall around too much, so I will fairly quickly go through this. You have some subset U of A, and this is detachable in the sense that you can decide membership for all elements of A in B, and therefore if you have this decidable binary capability, you can wrap this into a characteristic function. This is of course a member of this space. In the set theoretical coding, this is a subset of this product, and membership is then this, which was already assumed here to be decidable, expressed as just checking the function values. And now here you see this construction. I will not step through all of this, just take a look at the screen right now. I can use this element, I call it here a new variable letter rho, which is exactly from this characteristic function space, as we might call it, we can use this to induce a subset. So this is going in the other direction. We have the function, and we isolate with the separation this subset. And now here is then the coding of the classical. Here's the coding of a power set notion, which because we're dealing with functions, corresponds to the detachable subsets, which classically are all the subsets. So the set is here defined as the collection of all sets such that there is actually a characteristic function such that the corresponding set in the way we just defined equals this set, right? So this is taking this the mapping from characteristic function to set that we have just written down here. This is a mapping in the sense that we have a relation, a predicate, a binary predicate, which we can use in the replacement axiom to create the class as an set that is the image of this mapping, right? So, I mean, if you do not have it in your head, maybe look up again the replacement axiom. It says you need a functional relation, and then you get a set out of it. And so in this way, I also define here, this is, you have to track a little bit, what does your theory say? Is this a set, is this a class? But here, for your understanding, you define this a function here. I leave it open, or if it's a class or a set, it doesn't really matter, because with the replacement axiom, we just need the functional relation, and then the image is indeed a set. This is this. Okay, yes, so these are by construction, because I use the characteristic functions, only the sets for which we can actually decide the membership. So if you're in a constructive theory where we go through this whole definitions, then indeed this object exists, right? The power, the detachable subset power set. This thing exists, but while classically this is exactly the same as just the power set, because every set is a detachable set. Constructively, this is a priori we might say like a subset of the power class, right? If the power class is the class that contains all subsets of a set, then the ones which are detachable with respect to A are just some of those. We can actually write down predicates for which we do not know, or our theory is too weak to actually decide membership, and our theory is then not strong enough to prove that these non-detachable subsets are members of this thing that we've just defined. Okay, and while our theory will not be able to prove the existence of the power class as a set, we can go a little bit further than that. And this is also what you then find in this work of Ziegler here. So we will basically go through these definitions, and in a few minutes you will actually understand what is happening here, what all this thing mean, and how this is richer than just the detachable subsets, but still constructively not the same as the classical situation. I want to mention also here we have here this class notation where I say the power set of A is all subsets without condition, a trivial proposition. I just want to say this is a priori informal, because this is new notation, right? If you have on this side a subset. So what we did above with the image is technically speaking also just notation, but we mean this in the sense of having used the replacement axiom with this functional relation. And I write this down because this is what we end up generalizing. I think, this is actually also used here. Okay, so now we come to the class of truth values. In this context, the truth values will also be sets, and they are fairly rich. Again, this is this hiding stuff that I talked also about in other videos. So I scroll up. This is exactly what I talk here with squashing theories and hiding algebras, and this shows up in an even more generalized fashion in categorical logic. We will not make much use of this order structure of this class. We just want to understand how these truth values are characterized, ramified in the set theory here. So I start slow. I say, hey, if a T is a member of omega 2, which is just the set, the Neumann ordinal 2, the set which has the members 0 and 1, then, I mean, this is just what it says here. T is either 0 or 1. This implies, in this one direction, that every member has the property that all its properties are members of 1, right? I mean, if T is empty, then this is trivial. If T is 1, then the member is exactly 0, and this is exactly true. And so, written down differently, these members T, 0 and 1, are exactly subsets of 1. I mean, this is at least classically very, very trivial. And we take this as the definition here in this video as the truth value. Any object which fulfills this, which is a subset of 1, is truth value. And now you should think again now of this relationship between predicates that we had before and subsets. Here, this thing comes in. We will, in a constructive setting, not be able to prove that every truth value is either 0 and 1. And so suddenly, truth values are a rich concept because we can take any predicate and look at the subset of 1, and this is some truth value that might be equivalent to some other other intentionally defined truth values or not. And this is where the wild big structure of this class of subsets of 1 comes from. In the constructive setting, you don't have excluded middles, so you don't have the I hope I pronounce it correctly, trichotomy. I mean, I don't know how you translate it properly from German to English, but you do not have this disjunction of excluded middle, and likewise you cannot say that for all ordinals that either in two ordinals either they're the same or one is smaller than the other. You do not have this, so a lot of the structure of these ordinals is not there, and also the ways in which you can nicely define them is obstructed. One good definition is to say an ordinal, Neumann ordinal in set theory, is a transitive set of transitive sets. This classically is, of course, also exactly the ordinals, and we will use this definition here. And again, because we have a richer subset structure in a constructive setting, because so much fewer sets collapse, we have also like bunch of set definitions that you can read as new ordinals, and therefore you lack this, for example, the well order. Not even the natural numbers is well ordered in this context. Yes, but we want to speak about sets of truth values in this video. So in particular, I said that a truth value is a subset of 1. I already indicated the collection of all these, right? The collection of all subsets of 1 is actually a class, and the theory does not prove this to be a set. It's like a rich object. But to go further with the power class, then just looking at the detachable sets, we will actually, spoiler, now look at a bigger space than just the characteristic function space. We will actually choose sets of truth values and look at the functions from a set to this general sets of truth values, not just characteristic functions in the sense that they have like two possible outputs, but actually into any given set of truth values of which we already know that it is a set of truth values. Okay, a set of truth values is one where the elements are all truth values, i.e. where all elements are subsets of 1. And now this reification. So I introduce here the two letters P and Q. P shall denote a predicate and Q a proposition. For example, if I have a fixed value A, then a good proposition to think of is the predicate evaluated at P. And now what we do is we do this in the meta theory, of course, right? Because like in the first order theory of set theory, we do not have a proposition variable Q. Like we cannot like quantify over them as easily. So this is basically introducing notation. We say here, given any proposition, we define these double brackets, and you can think of sort of the reification realization kind of language. Where you just write it down like this. Here, if Q is a proposition, it does not even depend on X. So this thing is as complicated as it is to prove the truth value of Q, basically, right? So by definition, these are like some special cases here. I mean, by definition, it holds that this thing is a subset of one. I mean, this is literally defined by some separation axiom as a subset of one. Different theories might have different opinions what actually is allowed in separation. The like one conservative constructive Zermelo-Fraenkel only allows you to use proposition in the separation axiom where the quantifiers go over sets, i.e. are bounded. And other theories, like other intuitionistic theories, might be a little bit more lax. I don't specify this more here, but let's say just separation is allowed for whatever Q we have here. This is by definition, and also if Q, the proposition is provable, right? Then this is just true, and then this X can only be 0, and so this happens to be exactly the set which contains the number 0. Which in this case, it just is number 1. And likewise, if you can prove that Q is false, then no element makes it into this subset, and so this is 0, right? So these are the classical special cases. But as I point out here, even in a classical theory, you can use more complicated propositions of which you cannot like prove that they are true or not. And the go-to example, of course, is like the consistency of the theory that you're dealing with itself. So if you define this thing, this is still a subset of 1, but your theory can neither prove that this is the set 0 or the set 1, the Neumann 0 and Neumann 1. And constructively, if the theory has the disjunction property, right, I discussed this in other videos, then it is also the case then that this truth value, right, this bracket con t is a truth value by our definitions, and our theory cannot prove that it is actually the empty set or a singleton set. So it's actually, you can think of it as some set in between, right? If you think of the Heiting structure of the order structure, then this con t set, this truth value set, lies somewhere on this order structure and this Heiting ordering. And this is the sort of truth value that we play with. And of course, this is a set. We could package this whole thing into a singleton. Then we have a singleton that contains a truth value of which we don't know if it's 0 or 1. A priori, it's neither. And then we have a set of truth values. So while the class of all truth values is not provably a set in our theory, certain truth values we can package in set brackets, and then we have a set of truth values. Okay, and so from now on, we will use this symbol omega, which shall contain in all of our applications. It will be a set of truth values. It contains the 0 and the 1, right? So the extremal truth values, it contains it. And then it might contain some other truth values t, whatever we have already established to be a set. So for example, in constructive Zermelo-Fraenkel, for every predicate that is only has bounded quantifications, which might be as complicated as con t, but these are predicates which we can use to reify sets, these predicates into these truth value sets, and we might collect them. Okay, and yeah, here is this sort of notation and I teach you here to be able to read it, right? I teach you this because this is also what you will find, for example, if you read here page 100 of Ziegler's PhD thesis. This is this sort of expression here. I'm following what he does here. So this says for all element in a given set A, the P of A is in there, and this just then means that all the possible truth values that are created with this P of A, right? This P of A, like this is some proposition, right? And these are all truth values which are already known to us, in the sense that we have already established that they are, like, we have already collected them in our capital omega of choice here, right? This is a set in the following. It is not necessarily as big as the class of all truth values, but we know these omegas. And this says that all truth values of P on A are known to us, in the sense that we have been able collecting them into an omega. So they are T small, right? Because I mean, okay, 0 and 1 are simple. Like all theories have them, and we have T established as a set of truth values, and the predicate is T small on A. Okay, yeah, and here, of course, if by definition we said that our omegas will always contain the extremal values 0 and 1, and so if excluded middle holds, then this thing, as we established above, is always just 0 and 1, and so they are always in there. So anything that's behaving classically is really small. Okay. Okay, and now we are generalizing away from P2 or P omega 2, right? This was the set of detachable subsets. We use as predicate P, what we called more generically P before. We just use this membership relation. So basically X functions as a new predicate. And here observe, if we write down this kind of thing, the elements of that in A which fulfill the truth value equals the top truth value, then this is exactly the intersection, right? So this is, clearly a subset of A, and also it is those A's, small A's, for which we can actually establish that they are also in X, right? So this is exactly this. Of course, if X is already a subset of A, which is the situation that we want to talk about, then this thing is just X. And so we have just another way of writing X, right? X equals the separated out little a's such that this thing holds. And we do this because we want to emphasize that this bracketing, this operation of reifying predicates, in this case this membership predicates, to a set, is exactly what does the same job as the more special characteristic function previously did, right? We take this X and we create a function which looks at, hey, what is actually the status of membership, and if we can establish that it's in there, we assign a 1. But now we have established a language where we abstract away from just this binary truth value, this bool, but we also allow ourselves to use any other truth value which we already managed to capture in our theory in a set T. Okay. Yeah, so in this fashion of talking about this bracketing as a sort of generalized characteristic function, this statement, what you see here for all A, the reified, like this set-made predicate relation being in our omega, which is a set in the context we talk about here. This is basically like a totality statement for a function, right? If, like, to the extent that you view this mapping from A to truth value of A in X as a mapping, as a functional relation. Predicate, this is just saying, oh, we are total. This characteristic function is total, right? And yes, and so we are basically in the same situation as before. We say, where have I written down this? So we see this mapping as our characteristic function, a new characteristic function. And as before, we define for a characteristic function now in this bigger space, not from A to the Boolean set, but from A to our more general omega, big omega. Big omega does not have to be omega 2 with just 2 values, but now can have t. We do the same operation, we do replacement, and define the power set with respect, like conditioned on our set omega of A as the image of this kind of thing. And then this is the next, like in this more informal notation where I use here X subset A, this is exactly this kind of thing, right? And this is exactly now what we have here. Here I think it's called modified power class in this PhD thesis, and then in these talk slides here, this is also implicitly used, right? We will get to the construction of this modified hierarchy, but here is also, of course, this power class used, and that's why you see I think, this is not fully rendered. I now see there are some brackets going on, and I think here there's some stuff missing there, but okay. Let me see. Okay, this is just the next slide. So here, this is the 2. This is, okay, we will get to this. This is basically, in our stage of explanation, this is our T. So, okay, without dwelling too much on this, here you can look at the screen. I'm just establishing a bunch of relatively simple notions of in which case this power set that we've defined, right? We just used exponentiation, separation, and replacement. So even in a weak constructive set theory, relatively weak compared to Zemilo-Fraenkel classical, these are sets. They are not the power set from the classical theory because we have conditioned them on a set of truth values which is not provably binary, but it's actually bigger, a priori bigger than the binary operation. But we do not have the power class. We do not have the power class axiom. We have just, by replacement, abused the exponentiation axiom to get something which behaves a lot like the power set operation. And classically, this is the power set operation. But we had to do a lot more work here in the constructive setting to get this thing. And it's fairly rich because, by our assumptions, we have the classical truth values 0 and 1 in our omega, and so we have the extreme situation, the extreme subsets collected in there. And it's also the case that this is basically the statement here. Okay, we might also, like if you use this for some reason, you are in the situation where you have no power set of all. You don't have the generic power set, but you actually want to use something that is broader than just the detachable sets. Then you may or may not want to actually union this set even with A, so you have even more of the sets collected. But this will happen explicitly in what follows, namely the von Neumann construction. Okay, before we get there, this is some note on ordinal analysis where I just collect, in case you are like a classical mathematician and you want to understand, what is safe in the constructive framework. I've collected here like some facts about the strength. This is basically from various papers that I've read over the last years, but I'm not working in ordinal analysis or anything like that. So I just say this because take it with a grain of salt, although I'm fairly confident that everything here is like bona fide correct, but I'm mostly just quoting these kind of things. I don't need them. I'm just telling you like where roughly the cutoff is in strength for the constructive Zemilo-Fraenkel theory. So it is the case that this is a theory which has semantics in which it is allowed that everything is subcountable. So similar to the Russian school of constructivism, where you postulate that effectively everything is like a subset of the natural numbers, or can be indexed rather by some subset of the natural numbers. It is also possible to interpret this constructive fragment of Zermelo-Fraenkel in this way, where all the objects that you talk about are fairly small from a classical perspective. I talked about this in other videos. This for me also the main appeal, that you can take the whole theory, even though it's a set theory with like uncountable sets. You can take it to be about programs, and you have the theorems. If you have something proven in this constructive set theory, then you know it's rather implementable because it has semantics related to realizability. And so in particular, it has like a relatively small proof theoretic ordinal, meaning as far as this theory is concerned, you cannot go very far with like recursive orders and all this kind of thing. The power like lacks there at one point. And so there's also like this ordinal cutoff beyond which I think it's difficult to even, it has to do with ordinal notations. I'm not strong in this, but you have basically like a cutoff where even if classically you would have certain countable ordinals that are just ordinals there on which are classically well ordered, now in the constructive theory, the theory does not know or cannot prove that a certain order structure is there recursive, and you do not have to write ordinal notation expressions to even make them bona fide sets. And so the cutoff is fairly high for constructive theory, but from a classical perspective it ends somewhere fairly low in the countable range. And the first uncountable ordinal, classically speaking, is not a set, and likewise you can also in a sort of roundabout way talk about the class of hereditarily countable sets, and this also fails to be provably a set in this situation, in the constructive situation. And even classically, it's a rather more complicated object. But again, I have here some links. This is as usual linked in the GIST below. You can look at these resources, and there's also this ordinal analysis page where different strands of theories are listed. A link to the two authors which are particularly relevant to what I discuss here. I hope this gives you sort of an understanding where the thing cuts off. So I mean, this is still stronger than piano arithmetic as far as ordinal analysis is concerned, but you're ending somewhere in this countable range. Okay, and now finally let's talk about the von Neumann hierarchy. So I've first written down the classical definitions, and also of course classically holds. You have this nice relation where I will not go into like limit ordinals and all these very standard definitions there, but you have these certain relations, and this sort of relation here is mimicked again. We are now going to use our power set, the power set relative to some truth value set, and define this object that is also defined in the slides here. And I will list you just as I've taken them from the papers, and I've the things that are relevant for my next video as well. What you get and what you do not get with this classically defined index set. So with these objects defined here in the constructive setting, right? I mean, all the definitions that we make are also valid, of course, classically, because we're using the same first order language. But these definitions are just more complicated here because they are tuned such that even in the constructive setting, they fulfill certain things. As soon as you say, hey, I adopt lem, all like all sets of truth values that have 0 and 1 are just the dupleton, and everything collapses together and is super simple. And then this is the thing that we are just dealing here is von Neumann hierarchy. But I'm just listing which of its properties of the object that we have complicatedly defined here still hold in the constructive setting. Basically, you can just read what we have here. So I've listed here a bunch of properties. Oh, have I written down a definition there? Yeah, so we start in the same way. We start with the empty set as V0, and then we apply any power set to it, and we can collect all the hereditarily finite sets. The set of hereditarily finite sets, which is in projection with the natural numbers. This is the same object in both theories. And from then on, we apply our power set operation as we defined it here. And what do we take as the truth values, right? So again, we have our power set operation here, which we can apply to any set. And we need to choose some set of truth values. And then we can use it as a power set operation. And what we do is, in our construction of the von Neumann hierarchy, we also we have some V beta, and we just apply our new power set to it. Did I not write this down? Sorry, I'm actually confused because I thought I've written this down. Yeah, I think I just written it down like this. So what we do here is we take our V beta, which is some stage in the von Neumann hierarchy. We collect all the truth value which this stage already contains, right? So it will have 0, 1, and maybe some others. We use this as our truth values which are already established, right? And in this way, it's sort of bottom up. We say, oh, we have a V beta here. We take 0, 1, and everything that we already have as truth value, like reified as set. And we use this for our more generalized characteristic function notion, and use replacement to go like to a bigger V. Of course, again, I repeat myself. Classically, this is just a power set, because classically there's just these two truth values. But here we actually collect more than just the detachable sets, because if we would just use SP as a power set operation, the detachable set, then by construction we would only get these few sets for which membership is decidable, which constructively is not too many, right? This is just some trivial sets. But in this way, we have a certain strong notion of jumping to a new P. And we get these properties that are listed here. So we have this situation that if we have a relation between ordinals, then we actually go higher in this sense. The only caveat here is that we have to define these V's indexed by ordinals, and our ordinals are not linearly ordered, right? So we have now a lot of V's, and they can get very big, right? We can use a lot of power set operations on the hereditarily finite sets and go up. But it is not like a cone is in the classical situation. We have some sort of stray ordinals because we have a lot of other sets. We have another ordinals which we can also use as a starting point. And these will not be like, you should not think of it as the same sort of cone situation. I mean, to be honest, I don't fully know how I should like visualize it. It is just not the same nice hierarchy classical situations. But the whole like game that we played here is to still make sure that we have the objects that are classically the von Neumann hierarchy defined. As soon as we say, okay, from now on we'll use the classical setting, they collapse to the classical setting. And we have these objects for which there's this nice theorem that, did I write it down? I wrote my notes down a few days ago. So I expect I have written this down here somewhere. But the nice thing is that for every set that you have in our set theory, Ziegler here in his PhD thesis proves, you can look this up, he proves that for every set there is a V such that this is a member of it, right? So in a similar way as maybe this is here. So in a similar way as in the von Neumann hierarchy, where you can say, hey, eventually every set will make it into a V. You have a similar situation here in the sense that for every X, for every set X, it is member of some hierarchy stage. But again, it's with a caveat because it's not like as nice of a hierarchy. But nonetheless, I find this rather pleasing that even if you don't have the hierarchy in the sense, you still have all the objects that you have classically, right? Because again, if you postulate excluded middle, this collapse back to the object you already know. And so you can speak of everything here. However, again, with the caveat that you have a lot fewer sets, so you cannot go as high, and that's why people were writing PhD theses just 15 years ago about these sorts of situations. Okay, so I hope I didn't babble in too much. Yeah, here one last note. There was I saw some recent papers posted about equiconsistency between constructive Zermelo-Fraenkel and constructive Zermelo-Fraenkel, together with the postulate that the L, which is the Pondo of the constructible universe, that it contains all sets. Here I also want to mention, however, that it has been established that, for example, L does not behave as nice in this model, in the model theoretic sense, as in the classical situation, because it is not closed with respect to taking exponents, so it's not even validating the weaker constructive set theory. But nonetheless, I find this very nice because that it just means that you can express certain relations that you find classically, at least with these smaller ordinals in the constructive setting. And if you really want to make use of classical theory as well, then you can add them on the logic side. You just add it to the logic you add for certain propositions, exclude the middle to the logic, and then the objects which you were already talking about just have more nice properties. Okay, so with that said, the next video will be more classical in the sense that I will not talk about truth values and all these caveats of these constructions in the constructive setting, but we will talk about topoi in the von Neumann hierarchy. And in that sense, in the sense that talking about topoi is always adjacent to more constructive logics, it will also have to do with this. So I hope this was informative, and with this, I wish you a nice weekend.